Early warning systems are vital to mitigate the damage to life and infrastructure caused by natural disasters such as volcanic eruptions and earthquakes. Physical and chemical signals play an important role. For instance, seismic tremors and gas release can indicate that a volcano is about to blow. Now, geophysicists are developing a new tool which is both surprising and ingenious. It's possible thanks to muons, subatomic particles produced when cosmic rays collide with atoms high up in our atmosphere. Each minute, up to 10,000 muons from these collisions rain down on every square metre of the Earth's surface, ghosting through our bodies as we go about our daily lives. Muons have all the same properties as electrons, but have around 200 times the mass, which means they can travel much further through solid structures. By observing how this muon flux changes when passing through objects, researchers can start to build a picture of hidden internal structures. It's a technique called muography.
Muography is an imaging technique that allows to perform images of larger structures such as the domes of active volcanoes, or pyramids, or blast furnace, or nuclear power plants, and so on and so forth. There are a lot of use cases of this technique nowadays. How does it work? Basically, exactly like the medical X-ray imaging. You imagine that you want to make the image of this object. Then you use a detector which is behind the object. And what you detect is the absorption of particles that cross the object. Okay? In the case of medical imaging, the particles we use are X-rays. In the case of muography, the particles we use are muons. And how do we get the information which makes the image? Just by detecting the contrast between the different areas in the object with respect to the density.
The term muography was coined back in 2007 by Hiroyuki Tanaka at the University of Tokyo and his colleagues, who provided the first demonstration that voids and cavities within a volcano could be detected with the technique.
There are two strong points unique to muography. First, unlike other probes used in traditional techniques such as seismic waves, the muonic probes travel in a straight path through matter. This makes it possible to produce images with higher definition than other conventional techniques. Since they travel along straight lines, we can acquire the information about where exactly these muons pass through the volcano. This feature also contributes to reproducibility of muography. Secondly, muography gives us density variations inside volcanoes which cannot be measured with any other conventional techniques. Density variations are a driving force of volcanological dynamics such as buoyancy of magma. On the other hand, since muons cannot penetrate through deep regions of volcanoes, muography cannot image it. For example, the deep magma chamber. Chemical signals or seismic signals can transport in direct information from these deeper regions of volcanoes. Therefore, combining these traditional techniques with muography can offer a more comprehensive picture of volcanic activities.
In Europe, one ongoing application of muography is the Muraves project to build a picture of the interior of Mount Vesuvius in Italy. This volcano's most infamous eruption occurred in AD 79, where massive pyroclastic surges and ashfall deposits destroyed nearby Roman towns and settlements. Today, the petrified remains of inhabitants and their buildings are a popular tourist destination in the excavated towns of Pompeii and Herculaneum. Vesuvius remains an active volcano, and it's a dangerous brooding presence, particularly as it's so close to the populous city of Naples.
Vesuvius is an active volcano that after its last eruption in 1944 is in a closed conduit condition, meaning that the volcano is dormant. This condition is typical of Vesuvius, which in its long history has alternated between periods of inactivity like the current one to periods of frequent activity and frequent eruptions, often starting with the explosive eruption after decades of inactivity. The eruptive history of Vesuvius is well documented, and we know from the description and measurements how the shape of the volcanic crater evolved over time in the century preceding the eruption of 1944. In particular, we know that before last eruption, the volcanic crater was 2 times larger than the current one, and that the crater was filled by a lava lake that was partly eroded during last eruption. So the aim of the Muraves project is to produce an image of the interior of the Vesuvius cone and attempt to detect the denser part of the cone associated with the remains of the former lava lake. And this knowledge will contribute to understanding the dynamics of the last eruption and in general to understanding how Vesuvius works.
Over in Japan, Hiroyuki Tanaka and his colleagues have now set their sights on applying muography to another dangerous natural hazard: tropical cyclones, also known as hurricanes, typhoons, or simply cyclones, depending on where in the world they occur.
Like volcanoes, density variations or pressure variations are the driving forces inside tropic cyclones. If the pressure gradient is high, stronger wind is generated, but if the pressure gradient is low, the wind speed will be slow. In short, the pressure structure inside tropic cyclones will determine the strength of the tropic cyclones. Conventionally, we could only measure the vertically integrated atmospheric pressures. This is usually done with pressure sensors, which measure the weight above the sensor. Muons can measure horizontally integrated pressure by using near-horizontally traveling cosmic muons. This was impossible before. Since the tropic cyclone is actually symmetric, actually more symmetric than volcanoes, we can reasonably derive pressure distribution inside tropic cyclones. Once the horizontal distribution of the pressure is derived, we can calculate the wind speed distribution inside the cyclone. Thus far, we can more or less predict the trajectory of a cyclone. But it has been difficult to determine how a cyclone will evolve. Will it be stronger or weaker? What is the timescale of this cyclone evolution? Cyclomography will be the answer to these questions.
Find out more about the use of muography in predicting and tracking natural disasters in a feature article available now on the Physics World website.